Munson 352 gives us a configuration like this, where a flow is moving from left to right like this, from a pipe that's 0.1 meters in diameter over to a smaller diameter pipe with this pitot probe in the pipe. We've got a static tap here with a piezometer, and then we've got a dynamic tap here with this pitot probe, and we've got a height difference of 0.2 meters. And we've got this smaller pipe diameter D, we don't know what it is. And the question is asking us to find the relationship between Q and D. So what is Q as a function of this diameter and the parameters that we've got here? So first obvious thing is, let's try applying Bernoulli's equation. If we pick a point 1 up here and a point 2 here at the stagnation point at the entry to that dynamic tap, that pitot tube, then we should be able to write Bernoulli's equation along a streamline between 1 and 2. And if we do that, Z1 plus P1 over rho G plus V1 squared over 2G, same thing for location 2. First thing we'll do is we'll cancel out Z1 and Z2 because it's horizontal. We should probably cancel out the G's here just so that we don't have to carry them around with us. And we'll also wind up canceling out V2 because that's a stagnation point. So we're left with the pressure difference between P1 and P2, which we can calculate from this height difference, depending on the velocity at V1 squared. So if we rearrange that, we wind up like this. There's our V2 equal to 0 if we had carried it along with us. So the pressure difference over the density equal to V1 squared over 2. That pressure difference will be rho GH, where this is the H that we're interested in, here from these piezometer tubes. And the density is the same in both cases because this is water in the pipe, or some liquid in the pipe, and the same liquid in these tubes. So the densities will cancel out. And we're left with G and H and V1 squared. And it doesn't seem that we have D in the problem. It seems like D just doesn't matter. So this is a bit of a trick question. But if we follow that through, V1 is equal to the square root of 2GH, so it's just under 2 meters per second. So we know what the velocity is at this location. If we know what the velocity is, we can find the flow rate, the volume flow rate Q, as velocity times area. So Q is equal to VA. The velocity is V1, the one that we just calculated. The cross-sectional area of the pipe is pi D1 squared over 4. And if we plug in 2 and 0.1 squared here, we wind up with 0.0156 cubic meters per second. And that's true for any value of D.